felt like it was all over the place. It would be, I think, also helpful in grad school if they told you this is where we're going, because you just get like the first day it's sigma algebras. For a while it's just proofs on sigma algebras. You don't know where it's going. Then they introduce the measure and you still don't know where it's going. With the Borel sets as your first thing, and they don't actually have you work out and think about like what is it inside this Borel set. They just tell you these are the Borel sets, and then they just wallop you up the side of the head. So like it takes about a year to kind of figure out where this was all going. So hopefully we don't have a year to do this. Hopefully I can tie it together here. So we began with sigma algebras. They are the domain. And by they, I mean the sets in the sigma algebra are the domain of a measure. That's why we learn about sigma algebras. What are sigma algebras? Are they vector points? Sets. They're sets of sets. They're a set of sets. So pass around. Let's see. You don't have to be right or wrong. Just go to boards and see if you can remember the full definition of a sigma algebra.
You don't want us to look at our notes.
Yeah, don't look at your notes. See like how much you can actually figure out from memory.
That's why I take minutes.
You can peek at other people's boards.
Oh, it's sorry. I didn't see these over here.
These are good ones.
They're good ones.
Yeah.
Huh?
It's all good opportunities because I lost.
Thank you.
These are all right, but maybe some better. Yeah.
I've seen some dots. It could be more than just 3, right?
Memory means strength.
I can help.
What is? That is not, that's just a waste of resources. Man, have you seen this corner?
Let's see, in the rooms that have sliding boards, if you go right behind the sliding board, you'll see a whole bunch of stuff behind there. Erasers and. All right, once you think you're done, look around at others and see if you want to fill in anything.
Right. There's a good build on this. All those segments, yeah. Right, that's all. You can have a lot of right. You know, 3 days. I think I've seen this. You know that. That's how that's it. So much of that. We're not always paying so. Because they say. Sorry, look great.
All right, pig seeds. I just want to point out a couple things that it's for as little as we did, this is really good. You know, it's in my long-term memory. Like I'll probably have Alzheimer's and then be talking about sigma algebras. Don't they say like it's like parts of your memory get lost, but that long-term memory doesn't get lost? So if it ever saves me, I'll have a sigma algebra definition in my head. So a couple of things of good form. You first have to tell the reader what your sets are. F is a collection of subsets of a set omega that satisfies 1. Omega has to be in sigma algebra. 2, we say if then. So Carly has a if then on number 2. And I see that Lucas put a if then up there. He had the 2 parts. So you need if A belongs to F, then complement of A belongs to F. That property is, you want to write it that way because for proofs, you assume that A belongs to F. So you can use the fact that A belongs to F for whatever proof you're trying to do. So it's in your no. The third one is if A1 through AN ... they keep going forever, countable set of sets belonging to F, then the countable union belongs to F. In this case, that collection of sets is called a sigma algebra. Keep your notes. Again, you don't know where you're going to go. You might think, I'm doing infantry. I'm never going to come back to grad school. I'm never going to. And then, you know, there was two guys out of my Jedi math class that came back and taught here. And during Jedi math, I would have never thought those 2 were the ones that are going to come back here. So you never know. Infinite, right? In the case that the example I gave you for homework, there weren't infinite numbers, so you just had to show that the countable union of every common. Well, it was defined that way, so it was kind of set up. It's trying to help you set it up real easy. I confused my 104 type students in the other college by giving them the integral of 0 dx. I thought that would be easy. I actually got things from that, not 0. Second thing that the Borel sets was our first complicated example of a sigma algebra. Just to remind you, it's the smallest sigma algebra that contains open intervals. There's a lot of stuff in here. We started like just the tip of the iceberg, just putting stuff in there. It's like if open intervals have to be in there, we showed in class that X has to be in there for each X belonging to R. That means it's uncountable. There's an uncountable number of things inside the Borel sets because every single real number as a singleton set is in the Borel sets. And we also showed closed intervals were in there. And there's a lot of things They're uncountable. But it's not all of the subsets of R. So the Cantor set is in the Borel sets. That's an example of a set that's in the Borel sets. But there are subsets that belong to R that are not inside the Borel set. So even though it's massively huge, it's not all of R. And the way you show that is really hard, actually. I couldn't show it to the topology class, but the way you do it is you are counting uncountable things, and you just show there's less things in the Borel sets than there are in the power sets of R. And that's really hard to show you guys, but that's the idea.
It's less into uncountable sets, there's less.
There's less uncountable sets in the Borel sets than there are in R. And yeah, so you have to go through like first how to count things in an uncountable space. So there's lots of like math to build up to that point, but we actually learned that in the first year of my grad school when we took measure theory. Like there is a we call it non-measurable set. There is a set that's in B, that's not in B, that's in the reals. So it's not, you can't actually apply measure to it. Then we define measures.
And was there a time where people thought all of them was, and Borel sets did cover all of our?
There must have been, like these must have been papers that people wrote. So they must have been at some time. Kind of lets you think like there's stuff that to prove in math now that's left over is really, really hard. So we define measure next. The measure went from the sigma algebra sets were the inputs and the outputs were the positive reals or non-negative reals. Try it again. Go to boards and see if you can recreate the definition of a measure. Yeah, you are the positive reals plus 0. Yeah.
Can I get that other?
The previous one? You don't have to write it on your sheet of paper. I just put it, I just want to see like how far you can go with just remembering. So remember the things you plug in to the measure are the sets in the sigma algebra. So the measure has properties of, you know, what happens when you plug in those things from the sigma algebra. And there's 3 of them. That's the conclusion that we made after, like with the Lebesgue measure. That was the last class, but there's like 3 properties of just measure.
But is that only for Lebesgue?
That's for any measure. Not bad, Lucas. Not bad. Yep, you're getting there. Disjoint sets. You guys can take a peek at Lucas's board and then see if you can help him out for the last one. If you have disjoint sets, then
Send this to me. I just listen to it right now. I'm just gonna. Oh, yeah, this is. I'm just. I didn't know. It's very good. Oh, you can have, how far you get moved on? Did the human?
How much you get, Bridget?
I only remember the first one.
Well, now you have an example of a measure, the one that's empty set, empty set is 0 and everywhere else is infinity. That satisfies the definition of a measure. So the way I remember the definition of measure, it does actually link up with probability. Property number 3 is the definition of a probability measure. Like you have independent events, that means they're disjoint. Then the measure of the or this event or that event happening is equal to the sum of the events, the sum of the probability. So that's how I remember 3. And the first 2 are kind of like supposed to be that way. Actually, don't even have to put number 2 because I already said the range is R plus and union 0. And you need greater equals, not strictly greater, because you can have things that have measure 0. No, no. They just have to satisfy those 3 properties.
Wait, have a measure 0?
Yeah, I think we did that in class, right? With Dr. Das. We did a lot. It's a lot. Got 'em all? All right, so this is the full definition of a measure. I have no notes. And I think I came in here one day without notes. I left them downstairs in the office. I used to think my professors were just amazing because they would teach courses that were like 2nd year graduate student courses without a single note. And I thought, well, yeah, after you learn it, you really learn it. When we say we learn something, like you ever hear a plebe say, I know that. Like, what does that mean? Does it mean they saw it before and they recognized it? That's different, right? You saw someone complete the square, you recognize that that's completion of the square. It doesn't mean you really know it. If you can, they always say here, if you can explain it to someone else, you know it. I say if you can prove it, you really, really know it. You really know it. It's one more level.
Oh, we didn't learn that. We just used to.
Yeah, well, I got hammered on this stuff. I got hammered on this stuff. I think they say like 10,000 hours, spend 10,000 hours something, then you really, really have mastered it. I did. I was terrified that I'd get kicked out of grad school because I wasn't doing well in this class. We had a comprehensive exam in this class. So I decided not to go home for Christmas and stay there and just work problem after problem after problem. I kept it and I have all the problems I solved. And then I stayed the summer after the first year and just worked problems one after the other. That's why I know it. And then I took the exam in it and I still thought I did terrible. I had a bottle of vodka waiting for me. If I thought I did bad, I was going to drink that bottle. And if I thought I did well, I was going to drink that bottle. Yeah, it's stressful because, you know, by the time you're in 2nd year, one of our majors, actually, he's getting his PhD now at Baylor in statistics, and he has pure mathematics on it. And he was saying, you know, he had a pure mathematics thing. Major Turner, I don't know if he was here when you guys were here, but he was saying that, you know, he was so stressed out and he didn't pass it on the first time. So you get two chances. Like, you don't want to have two chances. You want to pass it on the first time. So he was terrified he was not going to pass it on the second time. And you guys have that condensed timing. You have to get it done. I didn't have that. I could probably petition to take it a third time, but still I was like really stressed out. By that time, you know you want your PhD. You know what you want to do. So if that's what you want to do and they say, no, that's not what you're going to do, we're kicking you out of here. That's terrifying. Okay, next thing we did. We were on number 3. Number 4, the next thing we did is we defined Lebesgue outer measure as the imp of sum of lengths. It was a really complicated definition. So here's the thing. Typically, you define the Lebesgue measure from the Borels. So you go to the Borel sets, define a measure on the Borels, which basically is length. If you have a closed interval, that is going to be B minus A. And then you extend the Borel measures to include some more sets, and that becomes the Lebesgue measure. But it's really hard. That's actually how I learned it. I learned that the Lebesgue measure was an extension of the Borel measure. And I went back and looked at that and went, we're not going to do that in here. We just can't. So I looked at this definition, it was actually more digestible. So that's why I did this one in here. It's a complicated definition. But basically what you really had to know is that the measure of a length of an interval is going to be B minus A. From that, you can do all kinds of other stuff. So we showed a couple things in class. We showed that the measure of a point in R is 0. And we also showed endpoints don't matter. So if I have measure of A to B, it's the same thing as measure of A to B, an open interval, which is the same thing as a half open interval, and so on and so on. So the endpoints don't matter. And then we also showed the measure with property 3 of measures that the countable measure of a countable set of points is going to be 0. That's what you had me for. And then Dr. Doss came in with Lebesgue integration. I think I might have just touched on Lebesgue integration, and he should have picked up from there. We really talked with each other about what to do next, like how to do it, because it's not like you can just pull a book. You didn't want to have him just spew out stuff. So we worked together on just what kind of examples we're going to show you. So he should have shown you a couple of things. He should have shown you the Lebesgue integration, but he should have defined it with characteristic functions. And then moved to simple functions and then told you that every function that you can think of on the reals can be approximated by simple functions, or written as a limit of simple functions, which should have made, he said that he felt like it made sense to you guys. They're like step functions. Yes, countable is always infinite. Sometimes we say infinitely countable, but when we say countable, we mean infinite. So that he should have shown you the Cantor set, which is an awesome, awesome set. It's like, we used it in chaos and fractals as an example of a fractal. It's used in this type of course for It's a countable infinite set. It's got all kinds of weird properties. The measure is 0 of that set. He should have shown you that because any countable set has measure 0. So it is a big set that has measure 0, but also feels like nothing should be in there after you keep taking out middle thirds. I don't know if he told you, but that stuff that's left at the bottom, the Cantor set, we call that Cantor dust. Okay, so the next thing we did is we defined the Lebesgue integral. For characteristic functions. I don't know why, but we use Hebrew letters for this. And you know, him and I didn't communicate about what letters to use. I'm pretty sure he used this though. So that's the definition of a characteristic function. And the integral of the characteristic function of x, we write d mu when we are talking about Lebesgue integration, not to be confused with Riemann, is going to be the measure of that set. And simple functions. And the integral of f of x in this case would be a1 times measure of a1 plus a2 measure of a2 plus dot 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 plus an measure of an. I actually do remember proving a lot of things using this cut up. So we had to prove properties about the Lebesgue integral. We'd first start with characteristic functions, show it's true there for characteristic functions, prove it's next true for simple functions, and then let f be arbitrary and the limit of simple functions. And then you prove it true by passing to the limit. That's how, like, we were on quarters. So in the second quarter, that's all I did is just prove like that over and over. Like, you got used to seeing that. Is this tying it all together? A little bit? This is really hard stuff, so. Cooper, you talked to Colonel Clark about this stuff? Because he loves this stuff. I'll let him know to bring this topic up with you.
He's not been working on it while I've been in his office. So
I'll mention it.
why does he love it?
It's part of a good stat program. Okay, so finally, Borel sets. Can be extended. To Lebesgue sets. It's called the completion, which is really hard to understand. But that's why I brought in the Borel sets. Everybody talks about the Borel sets. They're really well known. All the books on measure theory open up with Borel sets because it's easier to understand it, right? It's the minimal sigma algebra that contains open intervals. That's fairly straightforward. Considering what you have on the boards, it's pretty straightforward. Then you move to the Lebesgue measure and Lebesgue sets by taking that Borel sets and adding more things to it. It's kind of like field extensions, Isaac, that you had in algebra. You have something that's not a field, you want to make it a field, so you start adding ingredients until you get a field. So it's kind of like that. And then the last thing you saw was, as part of all this craziness, you saw construction of the Cantor set. So what do you guys think? Should we get T's that say I survive foundations of math and put a Cantor set on the front and then put like dates of all the topics we covered in this class on the back, like a tour? Maybe. And if anybody wanted that t-shirt, they'd have to come take the class. I'm serious. Would you guys buy it if we got that? It's funny. Oh, we could put like I survive foundations and now I'm Cantor dust. All right, we have 6 classes left. What?
Wow.
That's actually not much because you have Thanksgiving. Yep, it's not much left. So we have 6 classes left. So what I'm going to do in those 6 classes is I'm going to give a toe touch into real analysis for those of you taking real analysis. Just again, you don't learn math, you just kind of get used to it. Like think of the math that you learned back when you were in elementary school. You're used to it now, so it doesn't feel like anything. And I'm going to give heavy in-class assignments during that period so that, you know, we're like learning as much as we can in class. And you should use that time outside of class to prep for your final. There's a lot of points on it. It's also a signature writing assignment. And I did post it as well on the calendar invite.
No, I have seen me speeds. I mean, some speed here. Okay, so you need to come for the most speeds. Yeah, very required, maybe less than the size range.
Not that it matters.
This is supposed to be fun.
There's like ours pretty lighter. Your height is very big. Ours is within the 376, right?
Is that they're just like, let's
I
move it to get all up? Okay, they're trying to be helpful. It'd be best in your best interest to get it in on the final day of class, because then you don't have to worry about this anymore.
Yeah, so that's well, that's good. We don't mind that.
But if you want to extend it to T's and turn it into me and T's, that's fine. So here's what this is about.